So we start with a concrete analogy. I like to start with something concrete and something that we can picture. So I have this diagram here. It's related mathematically, but it's a different example, right? So it's a concrete. It's talking about solar panels. With a solar panel, you would want to orient it in such a way that the sunlight hits it and you have the maximum amount of area to capture the sunlight, right? Because you want the highest voltage from the sun. So you would have to orient the solar panel at a particular angle such that you capture that. And we can capture this idea by talking about flux. In this case, it'd be solar flux, light flux hitting it. And with an Earth diagram here, let's call this the horizon, north, south, east, west, you have different angles that refer to different points in the sky. So the angle in particular is alpha sub s, right? This angle that is the angle from the horizontal. So let's regard this line as the x-axis and how much it's angled. Where it's normal, the normal vector is the vector that is perpendicular to the surface of the surface in question. That vector is how far is that away from the x-axis? That's the angle that we're talking about. Okay? So with that picture in mind, we're going to talk about the electric flux in more detail with a problem here, with problem number 1. So going to problem 1, we have this one. Here we go. There we go. Can you all see it? Okay, so draw this in your notebooks. This is whiteboard problem number 1. This is the question. Let me zoom out just a little bit. This is the triangular box you want to draw. Can you guys all see that? Let me make sure the camera can see it. Yes. Okay. So, give a good sketch. Make a good sketch. And I'm going to take this drawing, this 3D perspective, and I'm going to draw a side view. And this is how we're going to do it. The side view is going to look like this. Side view. This. Okay, so, just a minute. Again. 30. From that side view, you guys could probably deduce that's the case, that angle there is 30. If I draw a line that is perpendicular to the surface, let's say the surface of interest is the slanted surface. You can see from this polygon that there's 5 surfaces. The slanted one, the vertical one, and then the 2 side triangles, and then the one on the bottom. But let's just talk about one surface at a time. Let's look at the slanted surface. So that slanted surface has a certain area, which we'll calculate later. But the point that I want to stress is, what is the direction? So what does that mean to have a direction? Given that you have a surface, perpendicular to that surface, we draw a line. That is defined as the normal to the surface, the area, the directional area vector, let's say. Directional area vector. If you want to draw proportionally, the length of that vector will represent the magnitude of that area. Now, how do we calculate the magnitude, right? We know the direction, but now we got to calculate the area. Looking at this is 30 centimeters, and we need to get 30 centimeters times this slant distance, right? Well, that's nothing than the hypotenuse of that 30-60 triangle, right? That's the hypotenuse. That's the length that we need. How do we get that? Well, if I know that this is 10, right, then I can say the cosine of 60 equals adjacent over the hypotenuse, which is what I'm looking for. So that's going to be 10 over h. So let's rearrange. H equals 10 over the cosine of 60. And we know cosine of 60 is 1/2. So 10 divided by 1/2 is 20. 20 centimeters. It's even the unit, so height, or in this case, the length and width, right? So I'm just using a different letter. The hypotenuse is going to be 20 centimeters. Okay, so calculating the area, it'd be 30 centimeters times 20 centimeters. That is 600 centimeters squared would be the magnitude of the area. The magnitude area. And then this is the direction. So, to find the angle that this area vector is from the electric field vector, we can put on our drawing. We see the electric field vector is going in this, let's call this the x-axis. This is the x-axis. So if I were to draw a parallel line like this, let's call that E, right? That's E. How would I find this angle here? Can you guys reason from a little bit of geometry what the angle would be? Well, if I extend, let's see here. If I, let's see, what did I do last time? I drop the perpendicular. I draw that parallel. Like that, you see how I drew I continued this line, and then I dropped the perpendicular. Okay, so let's see here. Well, that angle there. Well, we know that this here would be 60, right? And then let's see, let's draw this dotted line here, extend that. Then we know this here is 30. And then we know that's 60. You see how I'm going about that? Like I'm just slowly drawing the lines. I drew a straight line here to follow this, and I dropped the perpendicular, and I'm reasoning that that angle is this angle, and then 60 plus 30 is 90. Okay, that's good. And then that would be another 60 to make it back. So try and sketch that and understand how I got that angle. And then this 60, these are vertical angles, so this is 60. Questions? I'm going to pause there. You guys can see how I got 60 for that angle. Yeah, clear? Okay, so the angle between the electric field vector and the area directional vector is 60 degrees. Now here, let's introduce the formal definition of the electric flux. E, it's the dot product of two vectors, E dot A, and they're vectors. And to write that out, as much as some of you guys are probably like, yes, it's the magnitude E times the magnitude A times the cosine of the angle between those two vectors. And that's how to get the angle, you break down the geometry. To get the area, you just do your geometry again and define the area. Oops, I turned off. Come on. And with that, I'm ready to calculate my flux. Okay? So, what we do is we employ that function. So here it is. Let me erase what we have written. So you guys see that drawing. You can go back to the video and watch it. So now we see this. We have E times A times the cos of theta. And E, they gave us. The area would be, where was it? 600 centimeters. 600? Did I calculate that wrong? No, oh no, sorry, this is the wrong one. It's the next one. This one, there it is. There it is, this one. This one. Right? Okay. E times A times cos theta. E times A times cos theta. And we said it was 600 centimeters squared. I just plugged it in. And then we went to cos 60, and this should be this. The units of flux are Newton meter squared per coulomb. So that's the first part of that slanted surface. Now, I think you guys kind of saw the answer of the other surface, right? So going back to that drawing, let's go back to that drawing. Let's talk about the other surface. So let's talk about this. Let's talk about this surface back here, you see? This rectangular vertical surface, right? And let me draw that on the side view. So let's scroll over here, give some space. So if I have the side view, we would just see this, right? And then we saw the triangle again. And if I'm talking about this vertical surface, the area direction is what? It's going to be pointing this way. Right? It's not going to point into the object. It's going to point away from the object. That's the area vector of that other surface, that vertical surface. And then we have the electric field, which goes like this. Still going that way. Well, what's the angle between them? 180. 180 degrees. Using the same formula, it's going to be E, which we know, times the area, which we were given, 30 centimeters times 10 centimeters. That's going to be the area of that vertical rectangle. And multiplying them together, cosine of 180 is -1. So we get our answer to be the same value, but negative. See that? Voila. Now, is it surprising that the magnitudes are the same? That's the question I'm asking. You guys understand the concept? Is it surprising? Through the slanted surface, it was 2.34 magnitude. Through this vertical surface, it's also 2.34. Why? Yeah.
Same cross-sectional area.
Same cross-sectional area, exactly. If you were looking at it, you would still see the same rectangular window. See, when you rotate that slanted plane, exactly. When you're looking from this direction, so this is your eyeball. If you're looking in that direction, you see the same rectangle, same area. And then that cosine of 60 compensates for that to allow you to calculate that amount. Cool. Makes sense? That's why those two answers are the same magnitude, but they're different. Okay, so that's the first problem. And there's one more piece, which is well, we only did those two surfaces. We only did the slanted one and then the vertical back one. What about the two sides and the bottom? Well, let's do one of the sides. If I draw an area vector like this, that's going to be my area vector, the direction. And the electric field is this. Look at the angle between them. You see that? The angle between the area vector and the cosine and the electric field vector is 90 degrees. And we know cosine of 90 is 0. So the flux through the sides of this shape are 0. And same thing with the bottom. So let's try to draw this, visible piece. The bottom surface, the area vector would point down. And we see how that makes a 90 degree. You see that geometry in the head, right? So this area vector for the bottom flux would be cosine of 90, 0. So there's no flux on the sides, there's no flux on the bottom, there's only flux on the slanted surface and the vertical rectangular surface. That completes the explanation of whiteboard problem number 1. Now you guys have a really great idea, I feel, for doing that worksheet problem number 1 with the XY plane, the YZ plane. So give that a shot. I'm going to pause there. Alright, so this second problem, we have another equation that talks about electric flux. It's called the Gauss's law, which is that the flux, the electric flux, is going to equal the charge enclosed by some hypothetical boundary, which we call a Gaussian surface. The charge enclosed, abbreviated, divided by the permittivity of free space. So the permittivity of free space, I guess in a hand-waving explanation real quick, is that it's how much does free space allow, resist, how much does it resist the electric fields from permeating? But for the purposes of this class, you can just think of this as a constant, and it's 8.85 times 10 to the minus 12. 8.85 times 10 to the minus 12. And the units are going to be, well, let's figure this out actually. Charge. Charge is coulombs. This unit is what we're trying to ask for, but we already know that flux is going to be in units of Newton meter squared per coulomb, right? That's flux. That's the units of flux. So let's set this up. So Newton meter squared per coulomb. How can I get that to equal coulomb per question mark? See how I'm doing it? This is called dimensional analysis. So I just don't happen to know the units of epsilon naught. And let me just, it's annoying. Okay. So what do we do? Well, we're going to do, I have to multiply this over here, divide this under. So let's see. Question mark equals coulomb squared per Newton meters squared. See that? That's the units of epsilon. See, as simple as that. So the units have to work out. See how you do that? So anytime you're unsure about units on a test, let's say, but you can't look it up, that's how you can figure it out. Write the units, set them that they have to equal, this divided by this has to equal that, so then I just solve for it. And then that should be the units of epsilon. And that's permittivity of free space, and that's the number. Okay? So that's a nice explanation there. So let's go back to our main problem, though. Q enclosed. Q enclosed. There's 4 hypothetical boundaries, 4, let's say, Gaussian surfaces, and they enclose, the boundary encloses the charges accordingly. So S1 encloses this charge and this charge. S2 encloses all 3 of them. No, S2 encloses this blue one, these 2. And S3 encloses all of them, and S4 encloses none of them. So it's as simple as that. Section flux, let's look at this. Through S1, take a look at that. Let's just look at all 3 of them. Well, all 4 of them. Well, S1 enclosed the negative Q1 and the positive Q1. And then they just left it in terms of epsilon. I mean, you don't even have to plug that in. See? Look at S1. S1 encloses this charge and this charge. S2 encloses the positive charge and the minus charge. Yes, it does. See this blue circle? That's why the flux through that surface is 0. And 3 is enclosing all 3 of them, so you just add them up together. And then the 4th one, it's 0. Why? Because look at this surface. It's enclosing no charge. No charge is inside that surface. So this is really simple, but it's really powerful. The thing to take away here is that the surface that you draw is arbitrary. It could be perfect circles, perfect spheres, cylinders. It could be any shape convenient to the system that you're trying to solve. So you choose the surface, and then you can say, well, if I choose a circle, then I know that the surface area is 2 pi r squared, right? If I choose a sphere, then the surface area of a sphere is 4 pi r squared. So since you know the surface of specific shapes, use those shapes to figure out how much flux is going through. All right? So that's the second problem. Maybe you can see how to answer the second question. All right? Give that a shot. Okay.
Yeah.
All right, here we go. So, in this example, we have a cylindrical shell. I'm going to emphasize shell. It's hollow inside, it's a shell. And it's a radius of 7 centimeters and a length of 2.4 meters. And its charge is uniformly distributed on the spherical shell. The magnitude of electric field at a certain point is given by this, 36. So let me just write that down. It's electric field at 19 centimeters equals 36 kilonewtons per coulomb. And let's write the length equals 2.4. The radius equals 7. All right. We're asked two questions. What is the net charge? What is the charge on the sphere? We're asking the opposite question. Now we're not asking flux. We're asking what is the charge? And we can figure that out. And then what is the electric field at a point 4 centimeters from the axis? So we'll see. Let's turn this off. Okay. Let's draw this out. We have this going on. Okay. That's R. This is L. And the charge is uniformly distributed. Okay. We have our equation, our known flux equals charge enclosed divided by epsilon naught, and also flux also equals E dot A. Okay, we have those two. They're equivalent equations, and that means we can set them equal to each other. That's what we're going to do. They're asking, because the first question is asking, if I am 19 centimeters away from the axis, as they were saying, right? If I'm 19 centimeters away, either I'm here or I'm here, it doesn't matter. Let's say I'm here. That distance is 19 centimeters. At that point, the E field is given by this magnitude. At 19 centimeters, at that point there. That's what it's measured to be. Okay. Now, all right, now that I know E, I don't know flux. No, I do know flux. I don't know the area, right? I don't know the area. Let's just set these two equations equal to each other. Let's see what we get. We're going to get E dot A equals Q enclosed over epsilon naught. I just have to set those two flux equal to each other. Okay. We have E. What is A? Well, if I were to draw the area direction, right, I would, let's say I pick this point here, this point. This point, the area would point straight down, and the charge there would also point straight down. So the area vector, and then the electric field vector from some charge right there would also point straight down. And so those two vectors would be literally lying on top of each other. So the angle between them is 0. The cosine of 0 is 1. So at every point that's true, right? You can imagine on this cylindrical surface, you have area vectors pointing out, kind of like this. Let me draw it out. Kind of like this. So that. That. Kind of like a wheel with like spokes on it. You see what I mean? Like you have, at every point, you would draw an area vector perpendicular to that curved surface. And actually, that's the same picture as if you had charges on that surface. If you had charges on that surface, the electric fields would point in exactly the same way. So all the area vectors are parallel, or overlapping, the E vectors of the charges on the surface. It's the same picture. And therefore, all those vectors, the angle between them is 0. So we get here, let's say, okay, so we have E, we have A, so now we're just talking about the surface area of a cylinder. So that's the surface area. That's the surface area in question. So, surface area of a cylinder, we know that. That's going to be 2 pi RL. Why? Because, well, 2 pi r is the circumference of one circle, one ring, and how many multiples do I have of that? L. So I have that many rings, you know, like, and then count, that's the surface area. So that's going to be 2 pi RL, and then it's going to equal charge enclosed over epsilon. Awesome. If I were to multiply epsilon to the other side, I have my answer. You see that? So the amount of charge enclosed is going to be E 2 pi RL epsilon equals the amount of charge enclosed in that surface. Because the Gaussian surface that I'm drawing is going to be a cylinder. You know, imagine a bigger cylinder. You see that, the big cylinder? So I have a cylinder, and then you know how like the second problem I drew in a 2D case, we drew a boundary and we're enclosing the charge? We're now doing this in 3D. We're enclosing the charge with the similar shaped object. We're going to choose a cylinder because we have a cylindrical object. If we have a spherical object, like one of your problems, you choose a spherical surface. That's the area of that we consider. We want to make the area mimic the object's area, surface area. That's what we want to mimic. And then that will be the answer for the charge enclosed of this problem, plugging those things in. Okay, and actually let me just write that down just for record, for what that answer is going to be. It's going to be plus 113 nanocoulombs. That's what it's going to end up equaling after you plug everything in. Yep? All right. Now the second question was, what is the electric field at 0.4 centimeters from the axis? Well, this time we're asking 4 centimeters. So 4 centimeters is about like here, because that one was 7. At that point, what is the electric field there? Well, if I were to draw a hypothetical surface, a Gaussian surface, what is that small cylinder enclosing? It's not enclosing any charge at all. Right? Because all the charge was on the surface, because I said it was a cylindrical shell. So all the charges were on the surface. This Gaussian surface is enclosing, this boundary is enclosing no charge. And so if it's enclosing no charge, 0 enclosed charge, then it's 0. E dot A is not 0, but it's enclosing 0 charge, so that means for this equation to be true, E would have to be 0. See that conclusion? If I'm enclosing no charge, then the electric field at that point would be 0. Alright, so that helps you guys out with the third problem. Choose the surface area of a sphere to get that one.